right. I guess I'll start. So, right, when I was asked by the organizers to teach at this school, they asked me to teach about, the stuff I'd been working on some years ago, flux, vacua, and the things I've been teaching at in the Les Houches Summer School of 2007, which will indeed provide good background material for these lectures, even though there will be some there will be some overlap, but it won't be the same. So anyway, but I hadn't quite figured out what exactly it was I was going to teach about. So I tentatively called my lectures Vacua, thinking I definitely couldn't go wrong with that. But then I read Tom Banks' lecture notes, and so I have to call them minima. But I was thinking, well, actually, that's not quite right, because there's many ADS vacua of string theory. It's actually not minima of any effective potential, but they're saddle points. Okay, so actually I should call these saddle points. And I thought, saddle points of what? I mean, is this sort of some very classical notion, right? Whereas we want to talk about quantum mechanical states in a Hilbert space. So, it's like quantum analogs of saddle points. And I thought, well, quantum analogs of saddle points, that's just vacua, right? So I'll stick with that. All right. Very good. Well, so this is week 4, right? So you must be really sick and tired and oversaturated of all this physics. If not, there's something wrong with you and you will die alone probably. But so in order to kind of brighten your lecture, when I was thinking about these lectures, I came across this abstruse goose comic, which is really hilarious. I mean, I went through all of them; they're really funny. So, I thought this series. I mean, it's a series that will come is particularly appropriate because you can probably all identify with what will come, and also it's sort of a metaphor for the school, and it's also some sort of a metaphor or parallel for the stuff that will follow. So this was sort of the theme of these lectures. Okay, so it starts with step 1, begin. Step 2, enter the rabbit hole. Is this readable to anyone? Everyone? Yeah. Step 3, further down the rabbit hole. Step 4, gradual realization. Step 5, shock and awe. Step 6, frustration. Step 7, capitulation. All right. So, if you don't know who Snooki and the Situation are, you should look it up online. It's interesting. Maybe this will be the main thing you learn from this. Anyway, so, so in a certain sense, this is, sort of a mini version of, the whole course of acquiring more and more knowledge that mankind has gone throughout the ages. And, it has often been unpleasant because, we don't like it if there's just more stuff out there, more stuff to know, especially if there's like a component of randomness involved. We abhor that, okay? And so it all started, step 1, begin, Adam and Eve, they were hanging out, didn't even have to get dressed. In the Garden of Eden, this is the Garden of Eden, everything was simple and confined, okay? And then, there was this issue with the apple, and, they got kicked out, entered the rabbit hole, and this was rather unpleasant because it's like a big world out there and there's dinosaurs and shit. They didn't like that. But, they nevertheless ventured and, reproduced and spread over the planet and mapped out the world as good as they could. A little bit exaggerated on there, but and so there was this gradual realization that indeed, horribly, we live on this sphere that's just like floating there. It's a round ball, and we are somehow stuck to it. Okay, and worse than that, it's actually circling around this like bright, gaseous, hot ball of hydrogen and stuff. But it didn't end there. Right? People realized that we're part of some galaxy with an enormous amount of stars. In fact, this was already theoretically proposed 400 years before Christ by Democritus. First hypothesized that. And after him, several other people had this idea. But it had to wait for 2,000 years before it, got experimentally confirmed by Galileo, who just pointed his telescope at the Milky Way and was like, holy shit, there's all these little stars. Right? So, 2,000 years. Sometimes you have to be patient. Okay, well, but it didn't stop there. Okay, this is the phase of shock and awe when you realize that these galaxies are just part of like superclusters of more and more galaxies. And what this is not quite an actual image. It's part of the Millennium simulation, which here is shown at the largest scale. So this is basically more or less the entire visible universe, the matter distribution and galaxy distribution in there, forming this like funny spider webbish. Well, that's not quite a spider web. Like I don't know what it is. All over space. So in the entire visible universe, there's an estimated 100 billion or order 100 billion galaxies. Okay, so that's a lot of stuff. Now you can go back in time, and then everything just becomes more and more homogeneous, and you reach the point at about 380,000 years after the Big Bang, the surface of last scattering, where the universe became transparent, and this is as far as we can see, and this is, of course, the CMB as observed by WMAP. All right. So well, we can go further. We cannot see further, but we're pretty sure what happened before that up to some certain point. And so this is 10 to the minus 10 seconds. This is like very colorful because at that point color was deconfined. So that's more or less what it looked like. And I can assure you, I don't know if this works from there, but if you stare at this on your screen for more than 20 seconds, you get like really sick to the point of vomiting. So this is probably what the universe looked like. And that's not really true. Okay, and we can even go back to these ridiculously short times after the Big Bang, theoretically speaking, where we have the theory of inflation, just a scalar field slowly rolling in some simple potential, solves many of the naturalness problems that cosmology was initially confronted with, like the flatness problem, monopole problem, and so on. And moreover, it predicts fluctuations, quantum fluctuations, that give density perturbations which seed structure in the universe. And so this gives very specific predictions for the spectrum of the CMB, which I'm sure you've all seen, and the theory of inflation gives just an incredibly good match. So we're pretty sure, to very sure, that this is indeed what happened. Okay. Now, of course, if you have a scalar field rolling in a potential, it doesn't take too much imagination to imagine that this potential could have more than one minimum. Okay. And also you could ask, if this thing is rolling down, where did it come from? And also, this still doesn't explain what the Big Bang is. This comes after the Big Bang. Okay. Now, all of these questions, can find a satisfactory answer in this simple picture where you imagine that somehow, you have some initial state of the universe where the scalar field is sitting in this minimum, inflating very fast. And once in a while, due to some quantum tunneling effect, for example, it can happen that there's a bubble nucleated where, you get a scalar VEV inside the bubble that corresponds to this point over here. Once that happens, when this sufficiently large quantum fluctuation happens, it becomes energetically favorable for the bubble to expand, and thus, creating an entire new region of, new vacuum. Okay, so this is one possible picture of what happened before the Big Bang. So this whole process, in fact, we will come back to this later, will indeed look to an observer in the universe that gets created after this, exactly as the universe as we see it, at least if there's enough slow roll and so on. So in particular, the tunneling event basically corresponds to the Big Bang. Okay. Okay, now once you, and so this sounds all very, very nice and very plausible, but of course once you have accepted the possibility of having more than one minimum in a potential, then the step again isn't too large to imagining some high-dimensional scalar space with many, many minima. Okay. And then once you start thinking, well, where could this come from? Well, okay, a natural thing comes from some higher dimensional theory, maybe like some compactification. That's not a far stretch. This was already realized at the beginning of the century that this must be a logical possibility. But then you start wondering, well, or you should start thinking, well, okay, then there's another layer of non-uniqueness, right? Like, how do you compactify? What are the internal manifolds? These various, colorful choices you can make. And so, very naturally, you arrive at a bunch of very difficult questions, right? I mean, does this whole structure exist to begin with? How large it is? How large is it? What is dynamics on it? What is the quantum mechanics of it? Even harder. What is sort of the total global structure of it? Can we see imprints of it? What about predictivity? You want to compute the mass of the electron for whatever reason. Can we do this? Can we still do this? Is there maybe a notion of probability we should be thinking about? Is there a good notion of a measure on these things? Just what are just the general consequences of that? And these are very, very difficult questions, and has caused many otherwise sane physicists to just run towards walls with their heads first, trying to squeeze out inspiration, because it's very difficult. And so this is in parallel with abstruse goose, the stage of frustration for many. And, well, one possible answer to that is just capitulation. All right. So start just doing things which are fun and useful, who knows, and all of these wonderful things. And this is a great book, by the way. I'm a big fan. But however, I would like to say, there's actually some philosophical reasons, apart from, reasons such as like getting a job and stuff like that, philosophical reasons to go further down the rabbit hole, okay? And there's many, but, let me stick to three. So the first thing is, where our best theories, let's say string theory, fail most miserably, is where we are most likely to learn something truly new by thinking about it just a little harder, okay? So this is really, this is how progress in physics always has been made. And so that's a really good motivation to, just the fact that it works so poorly is a motivation to actually think about it. Okay. Furthermore, you can just study this thing by itself, as a mathematical object, some, like Platonic thing that exists, right, and it has these beautiful structures waiting to be uncovered, and should be uncovered. Okay, we should really think about it. It's not because it sort of has all these like horrible repercussions of our own nothingness compared to this infinity of possibilities that we shouldn't think about it. And who knows how will come out? These mathematical structures can lead to new insights, in other areas. Who knows? And and finally, we shouldn't forget that we have sort of the scientific moral obligation, right, to push beyond the frontiers of what we know, and beyond what we know, we are capable of knowing. Okay? I mean, if we are not going to do this, then nobody will, and so you just have to, right? I mean, this is why you exist. All right. Well, if this isn't convincing, then actually, while I was preparing my talk in a cafe here in Boulder, the Espresso Roma Cafe, which is actually a really nice cafe, a collection of misfits and wannabe misfits and great coffee and stuff like that. So I took a bathroom break, and what I saw there on the wall was very inspiring. It says, life is all about the things you'll never figure out. Okay. So I thought, wow. And then I saw a light. Well, actually, there is okay, that's not true. All right, so that's it for the fun. This is the tentative outline of this series. So I will start with explaining you what is the string theory landscape and how did we arrive at it. So I will give some prehistory, like sort of ideas that go back before string theory was discovered, which have been very influential in it. Then I will explain how the string theory landscape in its present state, with this like Rube Goldberg contraptions, complicated stuff, how that emerged and why it was necessary to get there, right? I mean, it's not that just it is for fun. Let's make it as complicated as possible to like piece of graduate students or something like that. It was just it was sort of the minimal thing that works is basically the situation we have now. And then finally I will briefly sketch sort of, or maybe not even sketch, some of the work that has been done after this string theory landscape came into like collective consciousness. Okay. So that will be a topic of today and maybe a little tomorrow. Probably a little tomorrow, I guess. So then I will get a little bit more technical and outline some specific models of landscapes. And I will start with gravity-free landscapes, okay, which are conceptually much easier to understand, as Tom Banks also has rightfully emphasized. But nevertheless, they're very interesting. So one actually example from outside of string theory, of course, is spin glasses. So there's a theory of spin glasses. Spin glasses, sort of the archetypical situation in physics where landscapes arise. And there's a beautiful theory of that, and these spin glasses are an amazing, rich structure, which leads to many interesting phenomena. So that's one example where you see that there's an intrinsic beauty in the structure of the landscape itself, right? Okay, so I'll start with that. And then I will talk about D-branes, but not like space-filling D-branes which give Vacua, but D-branes which are wrapping some internal cycles in some Calabi-Yau manifold, whatever, but which are localized at a point in space. So this has the advantage that you can actually, you're not constrained by tadpole cancellation conditions, so you can take the thermodynamic limit, which is always a good thing. And on top of that, these things give rise in low-energy effective theory to black holes. Okay, so once you at least switch on gravity, once you couple this to gravity, you get black holes. And so the study, the statistics, if you want, of the landscape of these complicated D-brane configurations gives rise to a microscopic counting of the black hole entropy. And I will show you this as an illustration of the the power of these techniques. Okay. Then I get to the conceptually harder part, which are gravitational landscapes that involve gravity, like true vacua, in which we think we live. I'll give some details about F-theory landscapes, which are, I guess, the best understood, at least for the purposes we want to use them for. I will also, since this is sort of the hybrid theme of the school, say something about how sort of landscapes of string compactifications get translated through the ADS-CFT correspondence to landscapes of conformal field theories with various properties, such as different critical temperatures for the phase transition to a superconducting state and so on. So you can just translate back and forth between these two landscapes. And then in the final part, I will talk about just everything, right? Like, I mean, these are just particular models that are well controlled, but we want more. Right? We want to be able to say what is sort of the most general landscape of string theory, vacua in whatever sense of the word. And there's been some recent work by Mike Douglas. There's also some pretty far-out work by mathematician Nabutovsky, who let me get to that when I get to that. Which is basically also part of this last part, which is given the fact that these things are hard and difficult, just how hard and how difficult are they, and are there just some perhaps intrinsic limits on computability that we should be aware of before throwing ourselves further down the rabbit hole? Okay, so that's the plan. Yeah. All right, so let's start with some prehistory, some important ideas, which very influential in the appearance of the string theory landscape. The first idea is, well, actually this is sort of a little disconnected still from string theory at this time, and this is sort of the idea of like when you look at the Euclidean path integral formulation of quantum gravity, there are particular saddle points, particular solutions, which are Euclidean wormholes. So these are just like tubes, which can just either split off like a little. This comes out of a paper by Coleman. I didn't draw this myself. Funny, maybe. So this is a little baby universe coming out of parent universe by some instanton, which is the wormhole. You can also have like some sort of the analog of a complete bounce, where the wormhole connects two different points on this Euclidean manifolds, and when these points are far apart, you can just think of it as if it's connecting two different parts of two different spacetimes altogether. Okay. And so these are solutions where, well, there's where you really have proper actual solutions to the Euclidean equations of motion are discovered by Giddings and Strominger. So what you need to get a real, so that you don't get the solutions of pure gravity. You need to add an axiom or like a three-form field strength to keep open the wormhole, but then you get perfectly acceptable solutions. Okay. Now, what these people then suggested is that these wormholes, induce laws of quantum coherence, and this is sort of, kind of. I mean, stuff can sort of disappear in the wormhole if you want to put it very colloquially, but definitely, if you think about it at first sight, you think, wow, I mean, the existence of these things in the Euclidean path integral is going to, when you integrate them out, is going to induce all kinds of horrible non-localities, right? Like, so you just integrate over these wormhole, collective coordinates, and since there's absolutely no barrier preventing the wormhole, to connect like arbitrarily far separated points, you expect some highly non-local interactions to be induced by that, right? So similarly to how an instanton, which is localized at one point, induces like local operators in the theory when you integrate them out. The wormhole, which connects 2 points, will sort of induce bilocal operators, and so you get stuff of this form. So this is just the wormhole instanton suppression factor, and these are just two operators, whatever they are, that couple to the wormhole. Okay, so some combination of fields, and so you see this looks very, very non-local and looks like very bad news. But as Coleman pointed out in '88, that's the wrong way of thinking about it. And one simple way of phrasing this is when you get something like that, then by the following simple trick, you can actually turn it into something local, right? So when you integrate out this parameter alpha, which is the constant, you simply reproduce this bilocal interaction, right? And so now what you get is, a term in the effective action which is completely local. You just have introduced a new parameter, alpha, which is like a coupling constant, except it's not constant, but variable, right? Because you integrate over alpha, and this is sort of like a probability measure, okay? Which depends on this particular choice of zero baby universe states you took. So it's not that this is sort of fixed by the theory, but this is just some initial condition, if you want, this probability, okay? And this is very, very analogous to how you get theta vacua from Young-Mills instantons, or how you get like block waves in a lattice. You get crystal momentum instead of position, and so on. So basically the true superselection sectors, the true states diagonalizing the Hamiltonian, are alpha vacua as opposed to like vacua with definite numbers of baby universes. Okay. But once you accept this, of course, since these wormholes they kind of couple to pretty much everything, you find that whatever constants of nature you started off with are no longer constants of nature. You scan over them. Okay. And so that is sort of the first, or like one way of arriving at some landscape, even though it's not a potential landscape in the broadest sense of the word, a non-uniqueness of theories of vacuum. Okay. Another idea, very different idea, but leading to similar conclusions, is eternal inflation, which, is, once you accept, the idea of slow roll inflation, and of course by now you have very good experimental reasons to accept this, is something you're led to almost automatically without introducing any new exotic physics. Okay, so how does this go? So working in Planck units, throughout the talk I work in Planck units. Throughout this lecture series I will work in Planck units. Okay, so when you have slow roll inflation, the scalar field just follows gradient flow. Okay, h is the Hubble constant, which in a slow roll regime is just equal to the square root of the effective cosmological constant, so the square root of the potential to some numerical factor. Okay, and now let's think what happens, when you let this thing roll for one Hubble time. Okay, so one Hubble time, 1 over h. The amount of field that will have classically rolled down is given by v prime over h squared, right? It just follows from this equation, right, for a time 1 over h. But at the same time, since you sort of have effectively something like a de Sitter universe, which, as you know, has some effective temperature, the Gibbons-Hawking temperature associated to its horizon, there will be some sort of quantum fluctuations or thermal fluctuations, which will make the fields fluctuate, right, vary. And these are the fluctuations. They're certainly real because these are the fluctuations that give rise to structure in the universe. In actual slow roll phase that preceded our universe, they were of the order of 10 to the minus 5 relative to the density, and they produce this plot of the CMB spectrum to very high accuracy, right? So they're definitely there, okay, and you can estimate their size over a Hubble scale simply as the Gibbons-Hawking temperature, essentially, which is given by h. Okay, so it will fluctuate by an amount plus minus h while it goes down. Okay. Now, at some point, in a regime where these quantum fluctuations could overpower basically the classical rolling down, right? And then this happens. So basically, this is roughly when delta phi quantum is greater than delta phi classical, or the same order. Pretty much half of the causal patches that get generated by this inflating universe will be fluctuating up, and the other half will be just fluctuating down or rolling down. Okay, but the point is, there will, because of exponential expansion, right? There will always be, places in the universe where the stuff keeps on fluctuating up and keeps on expanding and keeps on inflating. Okay? There will also always be regions, of course, where things fall down. So once you're in that regime, people say you have an eternally inflating space-time. Okay, so let's see if this can actually happen. So we had this estimate for the classical phi, which is this, for the quantum phi, which is that. The requirement that this is greater than this is simply v prime less than h cubed. H cubed is square root of v, so this gives this inequality. And if you look at the simplest possible potential, just m squared phi squared, right? You plug this in here, then you find that the condition to have eternal inflation is that m phi squared is greater than 1. Okay, we're working Planck units, remember. Right? Now, notice that if m is small, the mass of the inflaton is small, it's much smaller than the Planck scale, it's very easy to realize this while staying completely in the fully semi-classical regime. Right? You can keep this potential very small compared to the Planck scale and nevertheless have eternal inflation. Okay? So you don't need any exotic physics or any weird assumptions. So just within the realm of semi-classical quantum gravity, it happens. Okay. So given this, well, if you now imagine that this minimum that we're looking at is actually part of a larger landscape, potential landscape, you find as long as there are like channels at which this eternal inflation condition is satisfied, what you will see is that the scalar basically diffuses over the landscape, possibly reaching new minima, where it can sort of exit from inflation, and thus creating new universes, which may be very different from our own, because the scalar fields maybe have been displaced by a very large amount, and consequently also various couplings, Yukawa couplings, and whatnot, that depend on them may be very different. Okay. And so the picture then at a larger scale is that this sort of branching process, diffusion process, happens at all scales at different places, and the final result is at late times you get some sort of a fractal structure, which is sometimes called the multiverse. All right. Now, a variant of this, which I'm sure Tom Banks talked about, is the Coleman-de Lucia tunneling, right? Which I already mentioned. So the idea is you start in, you have a patch of space-time, inflating space-time in a false vacuum A. Right. So there's there's some constant quantum fluctuations, if you want, generating bubbles, where inside of the bubble you can have some scalar value which is located over here, and outside you have this scalar value over there. And there's two competing forces. One is that the one sort of is that this bubble can sort of lower its energy by generating more volume, right? Which is because inside this volume the potential is smaller. But on the other hand, when the bubble becomes larger, also its surface becomes larger, and so since the surface has a surface tension, this will give more energy. Okay, so there's two competing effects. But since area grows slower than volume, if the bubble manages to get sufficiently large, right, it can just classically expand and become bigger and bigger and bigger. Okay, so all you need is some initial quantum fluctuation that gets you over this barrier, and then a thing can just expand. So that's sort of the picture. Okay, more mathematically is described, more technically is described by some instanton, which was discovered by Coleman and De Lucia in 1980. And so the picture is this. So this here, the instanton itself happens in imaginary time. It connects to real time, where it starts expanding. So these blue lines here are, so this is time, this is space. The blue lines are the walls of the bubble. So they rapidly approach the speed of light. And inside of the bubble, because of the symmetry of this solution, the surfaces of constant energy density are these hyperboloids over here. Okay? And so what you get is an infinite open universe, basically, with an infinite amount of stuff in there, as seen by this observer, which is, importantly, negatively curved. Okay? So the imprint of such a thing at present would be would be the observation of negative curvature, except that, because inflation is so effective at wiping out all traces from the past, of course, this negative curvature, if ever detectable, will be very, very small. Okay. All right. And so the rate at which this happens is well, again, as usual, given by exponential of minus the instant function. Okay. All right. So this gives another mechanism kind of similar to the one I talked before of populating the landscape, but actually not requiring that these slow roll conditions are satisfied, that these eternal inflation or chaotic eternal inflation conditions are satisfied. Okay. So again, there's nothing exotic about this. Once you accept the idea of inflation, it's kind of unavoidable to have something like that unless something really weird happens. Okay. Which, of course, could be the case. But all right. Anyway, so this leads then to the idea of a multiverse, which was, in particular advocated by Linda and many others in the 80s. But the idea goes back at least to somewhere between 500 and 1000 after Christ in Hindu literature. It's talking about some God creating and annihilating universes, very much like Strominger's creation and annihilation operators acting on baby universes. So it's an old idea, and it's not difficult to come up with. So you have multiple causally disconnected effective universes with different effective low energy physics, and the mechanism by which they can arise, doesn't really matter. There's many possibilities. So we mentioned wormholes, eternal inflation is another one. But you could also just have, even if you don't have dynamics on this landscape, you could still have a wave function, right, which has different decoherent branches, each of which is localized on some particular vacuum state. Okay, so this is along the lines of many worlds interpretation of quantum mechanics of Everett, which is by all means the most conventional interpretation that you can come up with. Okay. So fine. So there's not really any problem with this idea. Now, of course, the things get tricky if you try to actually do something with it. And one reflex that people might have is just like, okay, well, there's like, maybe a wave function or this kind of stuff. There's some dynamics, so there should be some, we're already doing that in the time of the wormholes. So there should be some probability measure perhaps on it, and even though we cannot exactly predict, the ratio of the electron mass to the muon mass, maybe there is some probability distribution for it, and we can get, results from that. Okay. Now, first of all, this is not necessarily really the thing we want to know. I think the real question is like, is there this multiverse? Is there this stuff out there? It's sort of similar to, the great discovery of Galileo was, that actually there is this galaxy out there, these stars, right? He wasn't trying to come up with a cure for cancer from it or something like that, right? It's not that these things necessarily have to do something for us, but it's sort of, a very important question by itself, like, is this thing there or not? But anyway, so say, one way of maybe figuring this out is also to see if you could get sensible results from this, so fine. But you run into a big problem when you try to define probability measures. So for example, in the context of eternal inflation, right, as I was saying over here, right, so to an observer over here, for example, he sees an infinite, or she sees an infinite universe with possibly infinitely many observers, okay? And this is just in one bubble. There's also infinitely many bubbles, and this thing keeps on inflating forever. So there's just an infinite number of observers. So if you want to, for example, define a probability measure as saying, well, I just count observers, and then I see like how many observers see X and how many observers see Y. I take the ratio, and I'm done with it. That doesn't just work for the reason that there's an infinite number of them, and there's no natural ordering. Okay, so this is similar to the problem of like the question: are there more even or more odd integers? Okay, so we say, well, obviously there are as many odd than even. Okay, but this depends on how you order the integers. So you could take a perverted ordering and order them just like 1, 3, 2, 5, 7, 4, and so on, right? And if you then, count, the cutoff, you count, you take the ratio, you see that there are twice as many odd integers than even integers, okay? Now, of course, here there is some sort of a natural ordering, and so for that reason you would probably say, well, okay, there must be as many odd than even. But the problem is you don't have this in this eternally inflating universe, for example, because there's no canonical notion of time, for example, or of ordering, or of putting cutoffs. Okay, and a lot of work that has happened is sort of trying to come up with some sort of a natural cutoff that gives sensible results. Well, okay. So the most naive things that you try out, give ridiculous results precisely because of this reason. All right. Okay, so you can push this further, of course, and once you say, well, constants of nature are variable, you could also imagine, well, maybe also physical laws are variable, or maybe even logic is variable, and so on. And Max Tegmark has actually thought about this, and has come up with some classification of higher level multiverses, which is somewhat interesting. But we won't get into that. It's an interesting paper to contemplate. Okay. Right. Now, so let's now focus on some more technical issues, like why, what are sort of reasons to believe that this thing exists, okay? And why is it possibly a good thing? Okay. And, well, one of the great motivations is the cosmological constant problem, or cosmological constant problems, okay? And there are basically at least two cosmological constant problems. One is, why is it so ridiculously small, right? Why is lambda so much smaller than any fundamental energy scale would indicate it has to be? And the second one is the why now problem, okay? So this is basically the observation that apparently the vacuum energy density is exactly such that it has started to dominate more or less now, okay? It started to dominate maybe like at when the universe was like 5 billion years old or something, so effectively two cosmological scales that it's now. Okay, and just to emphasize how ridiculous a coincidence is, I wrote down this silly computation, right? So the vacuum, the time at which the vacuum starts to dominate, as I will explain in a little more detail in the next slide, is given by 1 over the square root of lambda in Planck units, or known as a cosmological constant, and t now is 14 billion years, more or less. Okay, so if you do this computation, you see big numbers. This is like the Planck time, and then this is like the number of days of the year, and the number of hours in a day, and the number of seconds in an hour. And you multiply these things together, and you divide, and you get 1. All right, which is bizarre. So why is that? Okay. So, well, of course, over the years, many solutions have been proposed to the cosmological constant problem. One of them, so the most obvious, is sort of, well, it's just dynamical selection by relaxation. We know systems, condensed matter physics, they like to go to their ground state, so why isn't it just like that? Okay. Now, there's many problems with that, but the most important one, or sort of crude one, is this works. You can actually cook up scenarios for which this works, but it will always result in a universe which is in its vacuum state, and which is cold and empty in particular, right? So something that is that is sort of cosmological constants dominated from the outset. Okay. In particular, there's no stuff in there. There's no galaxies. There's no temperature. I mean, it's basically an empty universe. Okay. So if you try to do this for a universe which is dominated by matter initially, right, which is a hot universe just like our own, well, the cosmological constant, the present cosmological constant, is a completely negligible contribution to that. So there's no conceivable dynamical mechanism that would actually detect it and select on it. Okay, so this is the essential problem in those approaches. Then, well, there is the idea of quintessence, and that is that, okay, the cosmological constant is not really constant, it's just some potential, just rolling, very, very slowly to a very, very small value. Okay. Now, that doesn't solve anything, obviously, because it actually makes the problem worse. There's double fine-tuning to do or quadruple fine-tuning to do. First of all, you still have to explain why it is that the scalar field likes to roll to 10 to the minus 120 m Planck to the fourth. Okay, fine-tuning number one. Secondly, you have to explain why this slope is so ridiculously small that we don't detect this today. Okay, so this is actually an even worse fine-tuning than just. Yeah. I'm of course oversimplifying a little, but this doesn't solve the problem. Okay. Another of these ideas that, well, maybe the vacuum energy has its natural value that you get out of loop computations and so on, but it just does not gravitate. Okay, you just modify gravity. Now, the essential problem that these approaches run into is that if that's the case, you really want this huge vacuum energy that you have to be completely unimportant at all stages throughout the cosmological evolution. Okay, otherwise you would have seen the effects of it. So that means you have to modify gravity at all scales. Okay, because of the history of the universe. But this includes scales where gravity is actually extremely well tested. Okay, and so you basically rule out, roughly speaking, these approaches just for that simple reason. Okay. So all of these approaches sort of failed, and the only one that actually led to something new, a computation that gave some result of some reasonable interest, is Weinbergs' argument from '87, which was before it was known there was a cosmological constant. Okay, and what he observed was something very simple. So, well, first of all, there are two important timescales we need to consider. One is the time at which vacuum energy starts to dominate. Okay. So when is this? Well, an easy estimate for that is, so in general, just from the FRW equations, you find that the Hubble constant, A dot over A, for matter and radiation and stuff like that, always goes like 1 over T. Okay, it's basically because the scale factor is some power of T for that kind of stuff, and so A dot over A is essentially 1 over T. On the other hand, for a cosmological constant, it's constant, and it goes like the square root of that of the cosmological constant. And so an estimate for when the cosmological constant starts to dominate is just to equate these two things, and then you find that it is 1 over the square root of lambda. Okay. All right, up to some numerical factor. Right. Now, on the other hand, the time scale for matter to collapse. Okay, so when the universe emerged, right, it was this quasi-homogeneous goo with small fluctuations on it, which, due to the nonlinear behavior of gravity, started to clump, right? Eventually, collapsing into stars, galaxies, and all the structure we see, and eventually yourselves. So now, what is the time scale for this to happen? You can actually estimate it just by doing a simple Newtonian exercise. So you just look at some expanding sphere, right? The present universe is well described by an expanding sort of particles, like explosion, like an explosion which has exactly energy 0. This corresponds to the flatness of the universe. So So it's just marginally at the escape velocity. Okay, that looks like a huge fine-tuning, but it's explained by inflation. Now, of course, there will be fluctuations. So somewhere at some regions, the mass inside of this exploding sphere will actually be a little higher than what gives you exactly zero energy. Okay, and so you could, if that's the case, then the sphere will not expand forever, these exploding particles will not expand forever, but it will just slow down, contract, and collapse. Okay, and this is when structure gets formed. So it's an easy Newtonian physics exercise to compute the time scale at which this happens, and that is basically given by the mass inside, the sphere that you're interested in of particles, divided by minus the energy that the sphere has to the power treehouse. Okay, this is a simple exercise. Now, the mass is a mass. Now, this energy deficit over here is caused by the fact that you have extra mass in this sphere, so there's extra negative potential energy, and this extra negative potential energy is just given by the mass fluctuation, delta M over R, right? Just Newtonian gravitational potential. Okay. Then you can rewrite this in terms of density, so M equals rho times R cubed times 4 pi over R or something, and similarly for delta rho, and now you see that the radius just drops out, and you get this universal time scale for gravitational collapse of some, explosion of particles with an overdensity delta rho. Okay. All right. Very good. So now, and so you see, well, if you think back at the universe, basically, these things are going to be set by the scales of inflation, right? Like the fluctuations here are set by the inflaton potential and the density as well. Okay. So it depends on some fundamental parameters that we don't have control over. Now, the crucial observation is very trivial observation, is that in order to get any structure at all, it had better be that the time at which the cosmological constant starts dominating comes after the time of structure formation, right? Otherwise, everything just starts accelerating and accelerating. Structure never forms. The universe just stays like, just collection of scattered hydrogen atoms, and that's it. Okay. Yeah. Right. Yeah. So this is okay. Exactly. So there is a right. So so this is all sort of average order of magnitude kind of estimates, but so even right. So if T lambda gets clearly when T lambda is much smaller than TC, then you just won't get structure. When it's very close, there's some crossover where you have like a little bit of structure, maybe like a star here and there, and so on. So there's this whole right.
But if space is infinite, then you have another counterfall because space is infinite. By the time I went away, I'll have an infinite structure even in this unfavorable case.
Well, yes, but that's right. So the input you can give this here. So this is if you start thinking about like, what is sort of the minimal requirement to produce life and stuff like that, maybe, right? But we don't have to do that. We can just take the data input that we see all the structure, all these scales, where it is, right? But even you could wonder, is this maybe possible that we just happen to be in some fluctuation, where there's a lot of structure, but then generically in our universe it is not the case. But it's no doubt statistically excluded, because if it was a rare event, what we would see is just like maybe our solar system and maybe a couple of stars, and that would be it, right? But we see actually the universe, which is pretty full. So you can exclude that. Okay. All right. Okay. So what do you conclude from that, right? Of course, Weinbergs' computation was more refined than that. He's very proud that he gets like some, actually this is all tape, but it's a beautiful computation, and it gets like 749 over 521 times this. So there's like all these numerical factors, which actually do matter, as you will see in a moment. But the basic idea is just this thing, right? Right. So what's the conclusion? Well, so you see that in the context, at least, of a multiverse with an extremely finely spaced vacuum energy densities, right? Like, so you have like all these vacuum, you have different vacuum energy densities with a spacing, you know, like less than 10 to the minus 120 times m Planck to the fourth. And you don't have any, like, you know, very sharp, like, selection features in the probability distribution. You do expect generically, you know, if everything else is kind of random, that the value of the cosmological constant will be of the order of 1 over the time scale for structure formation squared. Okay. Conversely, and this is actually what Weinberg was after initially, if you find that the cosmological constant is much, much, much less than this scale, then, you know, there must be some additional non-trivial mechanism at work that forces the cosmological constant to be small. Okay? And this is what these arguments always teach you. Like, you know, is there like, I mean, should we be surprised or not? Basically, this is all right. And at the time, it was not known what the outcome would be. Okay. All right. So now, just from observation, so since, well, this TC, as you saw, it depends on like the initial sort of what the inflaton potential looks like and so on. We don't know that, so all we can sort of go by is observations, and, you know, just from observing quasars, for example, we know that there was definitely structure at about 1 billion years. The universe is about 1 billion years old, so let's take this as a value. You plug this into this 1 over Tc squared, so you get 10 to the minus 117 times m Planck to the fourth. Okay? And the cosmological constant, on the other hand, by now we know is this value. Okay? So this is actually, well, it's remarkably close. There is, well, okay, you still are 3 orders of magnitude off. But, okay, you can sort of improve this estimate. I mean, there you get sort of, things get more complicated. Obviously, I have suppressed like all, you know, factors of 2 and pi and 547 over 719 and stuff like that. Also, you can sort of think more carefully about probabilities, measure choices, and so on, like Raphael Busso has been doing a lot of things along those lines in recent years. And that actually improves this estimate somewhat, depending on how much you're willing to swallow the assumptions. Well, you easily get it to just 2 orders of magnitude, and even, you know, like, well, when you get this, when you use a Busso measure, you pretty much smack in the middle of the distribution. Okay. So, you know, everything else considered, and considering the failures of all the other approaches, this is remarkable. Okay. Now, of course, it doesn't mean like, you know, there's nothing else to explain anymore, right? That's maybe sometimes here. So, I mean, what this computation shows is that basically, well, what this explains is basically the why now problem. Okay. Why is this? Well, you know, it's not so surprising, right, that we find ourselves not very long, you know, in cosmological scales after structure has formed. Okay. And, you know, because, well, if you wait for too long, like, all stars are just going to burn out, and, you know, that will be it. So, you know, so all observers pretty much live around now on this order of magnitude of time scales. And so you see that this relation lambda is of the order of 1 over Tc squared, automatically gives this relation between these 2 scales. Okay? So that's what this argument does. However, it doesn't explain, for example, why Tc is not smaller. Right? It could easily be smaller. We don't have an explanation for that. There are some arguments, you know, well, less convincing argument, but there are some arguments that it couldn't have been much smaller because it would have led to like too high density fluctuations in density, so we would, you know, get like black holes knocking our heads all the time and stuff like that, which wouldn't be a good situation to grow up in. But nevertheless, okay, so that's right. So these arguments have a very limited value, but what they basically do is they help to focus what the real questions are. Okay. All right. Nevertheless, what do we learn from this? Well, so that in a landscape with more than 10 to the 120 vacua, the naturalness problems of the cosmological constant are to a large extent eliminated. Okay. So this value of TC itself, which depends on delta rho over rho and so on, it looks like it's more like an initial condition issue, and it doesn't look like an extremely unnatural situation. Okay. It's maybe unnatural to the extent that inflation is a little unnatural. Now, naturalness has been a very successful guide in the past, right? Thinking of like how the theory of inflation came about, this came out of this big naturalness issue with the flatness of the universe, right? And that's why it was proposed among other similar problems. And while naturalness arguments are never a proof by itself, they should always be taken very seriously, right? And I would say that this simple Weinberg argument, it clearly means something, and it should be taken very seriously. Okay. All right. Now, that's all good and well, but am I running out of time? No, I go till 12, right? 12. Yeah, okay. So, but there's still this thing, you need 10 to the 120 vacua. Okay. So why isn't this just shifting the fine-tuning problem in there? As you can see, well, when you write down a potential like this, okay, well, this thing is 10 to the 120 vacua, but you would hardly declare victory in solving the fine-tuning problem of the cosmological constant, right? This thing just looks like this. So you get what you want, but it's not particularly satisfactory. However, there's actually a much more natural way of getting an exponentially large number of minima, and that is if you just consider some potential with, say, of the order of 100 or something variables, scalars, and if the potential is completely generic, you expect, in fact, an exponentially large number of minima. Okay. And so even with n of a few hundred, it's easy to imagine to get indeed 10 to the 120 vacua or many, many more. So that looks like a potentially promising idea. The question then that remains is, can this be realized in a fundamental theory, such as string theory? Okay, so this brings us then to the history of the string theory landscape. So how did this evolve? Okay. Well, the idea that, okay. So basically what we want is some potential, some effective potential in, 4 dimensions, which depends on variables, and a natural way of getting that, as you all know, is by compactification from some higher dimensional theory. Okay. This is not a new idea. Kaluza and Klein are most famous for that, but actually Nordstrom already figured this out in 1914, but this was completely forgotten afterwards. Which is maybe a good thing, because Kaluza-Klein sounds somewhat more catchy than Nordstrom-Kaluza-Klein. Anyhow, so what's the most general way of getting d-dimensional vacua out of like a capital D-dimensional parent theory? Well, is you just imagine topologically to split the space in two factors. You make a metric ansatz, which has the most general form looking like this. This is the internal metric. This is the metric that's seen from little d dimensional observer. Okay, we take it to be maximally symmetric in the vacuum state, so it's anti-de Sitter, Minkowski of de Sitter. And this factor over here is a so-called warp factor, which is allowed to depend on the coordinates of the internal manifold. Okay. So the original setup of this was reduction from 5 dimensions to 4 dimensions by these people, where it was observed that this gives naturally, so starting from just 5-dimensional Einstein, you get 4-dimensional Einstein plus Maxwell. Okay. In the 80s, these ideas had a revival in the context of supergravity, where there was some good reason to start in 11 dimensions. Okay. And then, of course, in the context of string theory, again, people were forced to consider these ideas seriously. Okay. So, right, so how did it start? Well, let's say it started when these people figured out that you could compactify the heterotic string on some Calabi-Yau manifold to get an n=1 theory in 4 dimensions. And so, of course, Calabi-Yau manifolds have since become very famous. So this over here, I found on some website, you can actually buy a Calabi-Yau manifold crystal. This button says add to cart. And I don't think these people at the time when they were writing this realized that this 25 years later, their discovery would be marketed in this way. They probably were thinking like Nobel Prize, but that didn't quite pan out. But anyway, so this is something you can buy. In no way affiliated to this website. All right. So, but in general, so what's a Calabi-Yau? Calabi-Yau is just some complex Kähler manifold which has a Ricci flat metric on it, and the condition for this to exist is that the first Chern class of this manifold vanishes. This has restricted holonomy, SUN holonomy for a Calabi-Yau n-fold, which turns out to preserve 1 over n-1 of the available supersymmetries. So if you start with the heterotic string, which has 16 supersymmetries in 10 dimensions, you compactify in a Calabi-Yau threefold, you get, no, this is completely wrong. This should be 2 to the n-1, right? Yeah, okay, sorry, there's a power missing here. So you end up with 4 supersymmetries in 4 dimensions, which is kind of what you want. It has cosmological constant 0. Okay, and the original one, which Andy run into when he was figuring these things out, is the quintic Calabi-Yau manifold. So given by this equation in its most simple form, modulo C star rescalings of all the coordinates. Right? So you just you define an equivalence relation, identifying these coordinates with some lambda times himself, some complex lambda. And so, okay. And so, so he first, he discovered this on Thursday night and thought, oh, cool, what a pretty manifold, and all these great things he will be able to compute from this. So then he sent an email to Yau saying like, well, is this the only Calabi-Yau, or maybe there's some more? And Yau immediately got to it and wrote him back a few days later saying that he had produced like a few hundreds of examples. So that's where this whole glorious dream ended. He was apparently very, very, very happy of squashing this young man's dream. So then the list actually rapidly grew, and it still grows. So it's actually not known if there's a finite number of Calabi-Yaus. In '88, there were like about 8,000 Calabi-Yaus constructed as complete intersections. So it means you have several equations in products of projective spaces. In '92. There was a classification of all Calabi-Yau threefold hypersurfaces in weighted projective space, where you don't have just a C star with single weights, but you allow the coordinates to scale in different ways. In '96, people figured out all Calabi-Yau 3 hypersurfaces in toric varieties, but this is still not like all complete intersections in toric varieties. There's probably many more still. In '98, when people started getting interested in F theory and M theory, people classified all Calabi-Yau 4 hypersurfaces in weighted projective spaces, of which, well, the elliptically fibered ones you can actually use for F theory vacua. And as you can see, there's quite a lot more. There's about 1 million of those. And, well, this stuff goes on. So if you, for whatever reason, want to, get to know these Calabi-Yaus a little bit more intimately, then you can look up like the database at this address.
The number was 500 million on the Calabi-Yau threefold hypersurfaces in toric varieties.
500 million?
Yeah, there's Kreutzer and Straka complex it four-dimensional polygon.
Right. Yeah. So, well, okay, but these are not hypersurfaces, right?
Pardon?
These are not hypersurfaces, probably. Well, these are polytopes. So first of all, there's not a one-to-one correspondent, and then second, it's not. Right. So this is restricted to. Right. These are hypersurfaces. Hypersurfaces in toric varieties. Yeah. By there? You distinguish, well, they're topologically, well, okay, I'm not even sure that these are really all topological distances. So it's not, so these are different constructions. It's not, so you know for sure, it's easy to see that they are really topologically different if their Hodge numbers are different, for example. But that's not a necessarily insufficient condition. So in principle, well, one topological invariant that distinguishes them is a triple intersection form in some canonical basis. So but so okay, they have gone beyond that, which is what you're referring to. But I'm not sure to what extent they're like complete classification results. One thing that is known about finiteness is that there's a finite number of elliptically fibered Calabi threefolds. So that's anyway, so there may be a finite number, maybe not. We don't know at this point. Okay, what we do know is that they have a very high topological complexity. So this is, for example, Calabi fourfolds in weighted projective space, and what this shows are Hodge numbers. These are like, the x-axis shows difference of these two Hodge numbers, the y-axis shows the sum. Okay, but the exact definition of these things doesn't matter at this point. The nice symmetry you see here is a manifestation of mirror symmetry, which exchanges H31, which counts the number of complex structure moduli, and H11, which counts the number of scalar moduli. But you see that these they easily go up to 300,000, meaning that these models have up to like 300,000 and even more scalars moduli. So that's a lot. Okay, in the last minutes, let me maybe give some early points of view. It is like 85, 86. So the famous one is Gross, Harvey, Martinic, and Rome in their heterotic strings paper. They said, although much work remains to be done, there seems to be no insuperable obstacles to deriving all known physics from the E8 times E8 heterotic string. Well, it's always good to be optimistic. Now, so Strominger, who had maybe the advantage of being brutalized by Yao really early on in his exploration of these things. Okay, at the conclusion section of another paper that he wrote shortly after, where he generalized, where he basically discovered flux compactification. So he generalized ordinary Calabi compactification to the case, including fluxes like form field strengths. So, well, let me maybe read it out loud. So it says the focus of this paper has been the mathematical properties of superstrings in torsion backgrounds, but we would like to conclude with comments on some physical implications. With the inclusion of non-zero torsion, the class of supersymmetric superstring compactifications has been enormously enlarged. It is barely conceivable that all zero torsion, so torsion is flux, that's what they called it in those days. Zero torsion solutions could be classified, and that the phenomenological acceptable ones, at the string 3 of them, might then be a very small number, possibly zero. It does not seem likely that non-zero torsion solutions, or even just a subset of phenomenologically acceptable ones, can be classified in the foreseeable future. As the constraints on non-zero torsion solutions are relatively weak, it does seem likely that a number of phenomenologically acceptable, at string 3 level even, ones can be found. And indeed, it is argued that some of the generic problems of the zero torsion solution are likely to be absent in many non-zero torsion solutions. While this is quite reassuring, in some sense, life has been made too easy. All predictive power seems to have been lost. But then he goes on, again, still being optimistic. All of these points to the overwhelming need to find a dynamical principle for determining the ground state, which now appears more imperative than ever, still the ground state. Okay. Well, all right. So let me stop here. I'm next going to argue that even though this looks like overwhelmingly many, it's still not enough. And but that I'll keep for tomorrow. Yeah.